We will begin the presentation of CSEC Multiple Choice Practice Paper 7 with Part A. Part A consists of the first 15 problems, going from number 1 through to 15. 0.875 written as a common fraction is, our problem is, write this decimal fraction 0.875 as a vulgar fraction. Decimal fractions are fractions whose denominators are powers of 10. The number of decimal places tells us the power of 10 concerned. The number of decimal places that we have in this particular case is 3. Therefore, the number of decimal places is 3. The power of 10 that we divide by is 10 to the power of 3, which is equal to 1000. The fraction is therefore the equivalent of 875 divided by 1000. 875 divided by 1000. The fraction may be reduced by a common factor of 25. 25 into 1000 is 40, and 25 into 875 is 35. We may have a further reduction by a common factor of 5. 5 into 40, 8, and 5 into 35, 7. The correct answer is option D. You may reduce the fraction in any way convenient to you. If you are more comfortable reducing the fraction by 5 each time, then do it. If you can see a reduction by 125, then there is no harm progressing in that manner. So the reduction of fraction is up to you. If you can see very quickly that you can divide through by 125, then do that. Of course, you will realize that the greater the number or the common factor that you divide by, the quicker the fraction will be reduced. But some students may not be able to see their largest possible common factor, and you may therefore reduce your fraction according to your ability. The number 3.14063 correct to 3 decimal places. We are attempting to write that number correct to 3 decimal places, focusing on 3 decimal places, correct to 3 decimal places. First, locate the third decimal place, and the third decimal place is located 3 digits to the right of the decimal point. Right there. Check the digit that is next in order of significance, that is the one immediately to the right, that one. The digit is a 6, which is of course greater than 5. We therefore add 1 to 0. If the digit next in order of significance is 5 or greater, then we will add 1 to the digit in question, which is 0. So 0 plus 1 is equal to 1. The other digits are not affected by the operation. So there we have 3.141. The correct answer is 3.141. And that is represented by option B. If the digit that we are checking is greater than or equal to 5, we always add 1 to the digit that is in the decimal place in question. If not, that is, if the digit is less than 5, we do not add 1 to the digit that is in the decimal place in question. So this is the decimal place in question, and then this is the one that we are checking to see if it is greater than or equal to 5. What is the exact value of 2 divided by 0.01 all squared? Before attempting to divide, let us find the square of 0.01, because we are dividing by the square of 0.01. 0.01 all squared, that's what we have. And we are saying that squaring a number is the same as multiplying 2 occurrences of that number together. So there we have the 2 occurrences of 0.01, and we are multiplying them together. When multiplying numbers with decimal fractions, we multiply the numbers as if there is no decimal place. Of course, we only have this one multiplying by this one in that event. So 1 multiplied by 1 is equal to 1. What do we do next? The answer will have the same number of decimal places as the problem. So the answer will be here. The problem is what we have here. 0.01, 0.01. 2 places of decimal here, 2 places of decimal here. A total of 4 places of decimal. The answer will therefore have a total of 4 places of decimal. There. This is one of them, and to complete the 4 places of decimal, we need to include 3 zeros. Now, 2 divided by 0.0001. From our work in primary school, we know that 0.0001 is equal to 1 over 10,000. The number of decimal places that we have here tells us the number of zeros that we should have following this one that we have here. We may write the arithmetic operation like that. 2 divided by 1 over 10000, which is 1 divided by 10,000. Dividing by a fraction is the same as multiplying by its reciprocal or its multiplicative inverse. So invert and multiply. Now we have 2 multiplied by 10,000, and the answer is 20,000. The correct answer is option D. We could have determined the answer very quickly by first realizing that when we square a decimal fraction, the number of decimal places will double. We are therefore dividing by a number that has 4 decimal places. The answer may be determined by increasing the dividend by 4 places of decimal. So just by looking at it, we may be able to write the answer down. Sometimes it is best if we just take a second to look at the problem instead of going very quickly to use a lot of mathematical principles or even to write a lot of information down in solving the problem. As we are saying right here, just looking at it, we know that we are dividing by a number with 4 decimal places. Therefore, the answer will result in increasing the dividend, which is 2, by 4 places of decimal. Again, there's no difficulty or there's no harm in making use of the mathematical principles that you would have learned in the early stages. Before attempting to divide, let us find the square of 0.01. Squaring a decimal fraction may be done quite easily by squaring the number without considering the decimal places. Then, considering that the square will actually cause the number of decimal places to double. So, square the number. So we are squaring just 1. If we square 1, we get 1. And what do we do next? Realizing that squaring a decimal fraction will actually cause the number of decimal places to double. So if we have 2 here, we will have 4 over there. And it is as simple as that. Now we are dividing by 0.0001. Recall also in primary school that when dividing by a decimal fraction, we multiply by the power of 10. That is required to clear the decimal fraction from the denominator. There are 4 places of decimal. We need to multiply by 10 to the power of 4. We need to multiply by 10 to the power of 4, which is equal to 10,000. We have to do the same in the numerator. So we are using the principle that in primary school, when we are dividing by a decimal fraction, we multiply by the power of 10 that is required to remove all the decimal places from what we have here. So to remove all the decimal places, we need to multiply by a power of 10 that has the same number of zeros as we do the number of decimal places that we have here. There are 4 decimal places here. We therefore need to multiply by 10 to the power of 4, which is 10,000. And if we do that to the denominator, and we want the fraction to remain the same, we will have to do that also to the numerator. In that event, in the denominator we have 1, and in the numerator we have 20,000. Any number divided by 1 results in the same number. Therefore, the correct answer is 20,000. And we have verified that option D is correct. Here we may exploit the beauty of multiple choice, which is all of the answers are there. In this particular case, we may use the fact that the answer is here already. One of these options is the answer, in determining the answer without actually multiplying this by this. Calculators are not allowed in the multiple choice examination. Therefore, we need to make all calculations mentally, or at most make use of rough work. No matter what we do, as long as we are not using a calculator, one of the greatest determining factors of the correct answer to this problem is the number of decimal places. The number of decimal places. When multiplying numbers, the number of decimal places in the answer will be equal to the total number of decimal places in the problem. The answer cannot be correct without the correct number of decimal places. So, if we do not have the correct number of decimal places, no matter what we do right, the answer cannot be correct. So the answer cannot be correct without the correct number of decimal places. Since no two options have the same number of decimal places, we are sure that the values of the digits in the answer are immaterial. So we are sure that these numbers, irrespective of what they are, has no bearing on the solution of the problem. We can totally neglect all of the digits that we have here and their values in order that we may arrive at the correct answer. So the correct answer will have the correct decimal places. Here, no two options have the same number of decimal places. Therefore, if we can identify the one with the correct number of decimal places, then we would have identified our answer. What do we have there? The total number of decimal places in the problem is 5. The correct answer will also have 5 decimal places. That is the only one with 5 decimal places. Therefore, that one is sure to be our correct answer. 1, 2, 3, 4, 5 decimal places. The answer 1, 2, 3, 4, 5 decimal places. That is the only one that is possible to be correct. It is our correct answer. The correct answer is option A. We did not have to multiply anything in order to arrive at the correct answer. That is how it is with multiple choice problems. Sometimes we may take advantage of the fact that the correct answer is always there. Identifying it may not always require any great mathematical feat. If $350 is divided into 2 portions in the ratio 2 to 5, the smaller portion is what we are attempting to find. We may first take an approach in which we consider that the total is divided into a number of units that is equal to the total of the numbers in the portions. So 2 plus 5, we have 7 units. 7 units is what we have. We may make use of the equivalence relationship between the total amount of money being shared and the total number of units in solving the problem. So we are making use of the total amount of money being shared and its equivalence relationship to the total number of units, and that we are doing in order to solve the problem. 7 units represents $350. We have the amount of money that is equivalent to 7 units. We may use this to find the equivalent of 1 unit, and to find 1, if 7 of something is 350, when we put 7 of them together we get 350. If we take 1, we are definitely going to have less. Therefore, we need less. We divide by 7. There's nothing to it. So 1 unit is $50, and we are looking at the smaller portion. The smaller portion is equivalent to 2 units, and we have 1 unit. We have the amount equivalent to 1 unit. All we need to do is multiply that amount by 2. 2 units will be $100, and that is represented by option B. Many candidates will have no difficulty seeing the 2 steps that are necessary in arriving at the answer and may take them in one. So some students will just 350 divided by 7 multiplied by 2, and they just get the answer in one step like that. But we are attempting to demonstrate the finer details of the principles that may be used in solving this and other similar problems. Here we go again. Candidates should be well familiar with sharing according to ratios. At this level, this problem should really be solved in one step and be done mentally also. The whole is represented by 5 plus 2, which is equal to 7 units. The smaller portion is represented by 2 units. It is therefore 2 out of 7. 2 divided by 7, or 2 over 7, 2 out of 7 of the whole, which is $350. So it's 2/7 of $350. And we may do that reducing the fraction by a common factor of 7, and 7 into 35 is 5. Do not forget the 0, so 50. Multiplying 50 by 2, we get $100. The correct answer is option B, as we have discovered before. From primary school, students are accustomed to solving these problems at sight. The only obvious mistake is calculating the larger instead of the smaller portion. Highly unlikely, highly improbable, but possible. So if we did that, we would say 5 over 7 multiplied by 350, and the result would have been $250, and we have it right here. Good. I like that kind of a gesture. The option for that answer is D. So if a candidate made a mistake and find the greater instead of the lesser portion, then the answer would have been there for the error that the candidate would have made. Always be prepared to take a good look at the problem to see if the answer is in keeping with what was asked. Good multiple choice items will always have one option that is the answer to the most likely incorrect way of answering the question. Right. So one option in a good multiple choice item. One of the options always represents the most likely incorrect way of solving the problem, and that is what I consider to be a good multiple choice item. If 60% of a number is 90, what is the number? 60% of that number is 90. What is the number? We can think of 100 different ways that a candidate may want to solve this problem. Finding 60% of 90 may be one of the ways. Trying to increase 90 by 60% may be another way. But the correct way is based on ratios and proportions. That principle. We have 60% of a number and we need to find the number. The original number is always 100% of itself. Never forget this. Every time you have a problem that has anything to do with percentages, do not forget that the original is your 100%. We therefore need to use 60% and the number that it represents in order to arrive at the original number, which is 100%. So use 60% and the amount that it represents in order to arrive at the original number, which is 100%. We may make use of the equivalence relationship between 60% and 90. in solving the problem. So 60% is 90. What is 100%? So 60% is equivalent to 90. We have the number that is equivalent to 60%. We may find the number equivalent to 1% by dividing by 60. That is always a method that we use when we are working with equivalent relationships. So find 1%. 1% may be found by dividing 90 by 60. And 1% will be 1.5. The original is 100%. We have the number that is equivalent to 1%. All we need to do is multiply by 100 because we need the original, which is 100%. So take the amount for 1%, multiply that by 100, we get the amount that is equivalent to 100%. That amount is 1.5. That is equivalent to 1%. Multiply that by 100, the result is 150, and that is our 100%, and it is represented by option C. Many candidates will have no difficulty seeing the two steps that are necessary in arriving at the answer and may take them in one. So 60% is 90. What do we do? 90 over 60 multiplied by 100 and we are done. So 1% is equivalent to 90 over 60. We did not have to divide 90 by 60. We could have waited for the multiplication by 100. Then reduce the fraction. So multiply that by 100 to get 100%. And then our answer may be arrived at. Reduce by a common factor of 10 by striking zeros from both denominator and numerator. So our first step is reducing by a common factor of 10. Then reduce by a common factor of 6. So 6 into 6 is 1, and 6 into 90 will go 15 times. Although it's a little bit obscured, I hope that you are seeing this 10 that remains here. So 1, 0, which is 10, 1, 0, that is 10, 15. Multiply 10 by 15 and we get 150. And that is our correct answer. The HCF of 12, 15, and 60 is a factor of a number, because we are trying to find the highest common factor of those numbers. If we are not careful, we will attempt to find the LCM. So here we are taking a look at factors. A factor of a number is a number that can divide into it without leaving a remainder. We will see factors of the numbers on the next slide. So a factor of a number is a number that can divide into it without leaving a remainder. And we'll get examples of factors when we are taking a second go at solving this problem on another slide. Common factors of numbers are those numbers that can divide into all of them, or we may say into each of them, without leaving a remainder. Their highest common factor is the largest number among the common factors. So we have factors are numbers that can divide into other numbers without leaving a remainder. Common factors of numbers are those numbers that can divide into each of them without leaving a remainder. Therefore, their highest common factor will be that number, the largest one, among the common factors. Demonstrating a knowledge of highest common factor, a student should have no difficulty seeing that the highest common factor of the numbers is 3 in an instant. So if we are sharp on our common factors and on our factors, then we should have no difficulty seeing that 3 is the highest common factor of 12, 15, and 60. But we may demonstrate the solution of this problem by making use of principles and mechanics that we all should be familiar with. However, we may find the HCF by making use of a table. Divide each number by the lowest common prime factor, then attempt to do the same with the results until no further division can take place. And again, do not confuse this process with the process of finding the LCM, which also makes use of a table. So in finding the highest common factor, the factor has to be common in the table, else we cannot use it. So use the smallest prime factor that is common to all of the numbers, and that is 3. So do not forget that we are attempting to find the highest common factor. Therefore, the factor that we are using here has to be common to all of these. That is, the prime factor that we are using here, or attempt to use, must be common to all. So 3 is the only one that is common to all. We use 3, and we will divide each one of these by 3. So 3 into 12 is 4, 3 into 15 is 5, and 3 into 60 is 20. Any other factor that we are attempting to use must be a factor of 4, 5, and 20. There is no other such factor. Therefore, we have exhausted our table. It is not the same as finding the LCM, in which we use all of the factors that can go into these. So in this event, we would have used a 2 first, and when we get to this stage, say that we would have been at this stage, we would have used another 2, because 2 can go into 4, or it may go into 20. That's not the same way that we approach the table when we are finding the highest common factor. Hopefully, by the end of, if not part A, then we will be able to find an LCM problem in the other section, in which we will attempt to solve that problem by making use of a table, and we will see the difference that we have with that method and the one that we are using to find the highest common factor. There is no other prime number that is a common factor of the results. No other prime factor that is a factor of the results. Therefore, the table has been exhausted. The HCF is therefore 3. Let us find the HCF of the numbers by using another method. This time, we will write down all of the factors of the 3 numbers and select the largest one that is common to all of them. Factors of 12 are those numbers that can divide into 12 without leaving a remainder. Let us write down all of the factors of 12. All of those numbers that can go into 12 without leaving a remainder. Factors of 15 are those numbers that can divide into 15 without leaving a remainder. Let us write down all of the factors of 15. Factors of 60 are numbers that can divide into 60 without leaving a remainder. Let us write down all of the factors of 60. In this exercise, we have proven to be a little bit monotonous, or we may say repetitive, but I think that by the time we are through, everyone should have gotten the point. So there we have all the factors of 12, all the factors of 15, all the factors of 60. Notice that 1 is a factor of every number, and that every number is a factor of itself. The largest number present in all three sets is 3. It is therefore the largest factor that is common to all three of the numbers. It is therefore the highest common factor. So the largest number present in all three sets, do not forget that these are the sets of factors. Therefore, the largest number present in all three sets is 3. So 3 is the largest of the common factors. It is therefore the largest factor that is common to all three of the numbers. It is the highest common factor. We need to determine the value of the digit 2 in 425.3. The value of the digit 2 in 425.3. The value of a digit in a number is dependent on two things. One, the first one is the value of the digit itself, and that is called the face value of the digit. The second one is the value that the digit has because of its position relative to the other digits, called the place value. Let us first place the number in question under the microscope. That is the number that we have in question. What do we imagine that we will do next? Let us take note of all of the place values of the digits in the number. Those are all of the place values of the digits that are present in the number. The value of a digit in any number is equal to the product of its place value and its face value. Do not forget that the value of the digit is dependent on two things, the place value and the face value. And here we have defined each one of them, and its value we are saying is equal to the product of its face value, which is 2, and its place value, and the place value is 10. So take note of its place value. Right. The value of the digit is 2 tens, and that is represented by option C. "99 multiplied by 101 has the same value as," and we have quite a bit of not necessarily confusing options, but some of them might not be so clear-cut. As a matter of fact, at appearance they can prove to be very cryptic. Apart from fidgeting with the digits, checking each option against the statement of the problem in order to determine which one is correct, we may do well solving the problem in a short period of time if we have an appreciation of the distributive law. So instead of fidgeting with the digits in order to see which one works out to give 99 multiplied by 101, instead of fidgeting with the digits in order to do that, we may come here and say, work this out and see if we get this, work this one out and see if we get this, and so on. Instead of doing that, we may make use of the distributive law. Right, it says here, if we have an appreciation of the distributive law, then solving the problem may be done in a short period of time. The contents of the options with the constant 99 throughout indicates that 99 should remain as it is. So notice that we have 99, 99, 99, 99, 99, 99, 99. Therefore, this 99 that we have here, we should not trouble that. We should cause it to be as it is. So let 99 remain as it is without decomposition or without decay. It is obvious that 101 has disintegrated into 100 plus 1. We will therefore rewrite the expression replacing 101 with 100 plus 1. So there we have the 99, the never changing 99. We have that with 100 plus 1. And what do we have here? That 99 is being multiplied by 101. So 99 is being multiplied by 100 plus 1. Multiplication is distributive over addition and subtraction. The sum of 101 is multiplied by 99. 99 will therefore be distributed to each term in the brackets. Distributive law says distribute this 99 to the 100, multiplication. Distribute this 99 to 1. So we have 99 multiplied by 100 and 99 multiplied by 1. As a matter of fact, we did not need to include these brackets. All we needed to do is just multiply. But the inclusion of the brackets make the expression a little bit more friendly to the eyes, and we have no difficulty seeing that this answer is actually option C. What is the largest number of plums? This is the one that we made mention of a little earlier on. The LCM problem as opposed to the HCF problem that we have just completed a few slides ago. What is the largest number of plums that can be shared equally among 6, 9, or 12 children? Just taking a look at the nature of the problem will cause us to conclude that any number chosen from our answer has to be one that 6, 9, and 12 can divide into without leaving a remainder. Because it says, what is the least number of plums that can be shared equally among 6, 9, or 12 children? Therefore, if it is to be shared equally, then 6 should be able to divide into that number without leaving a remainder, so 9 and also 12. One of the operative words is least. We therefore need the smallest number that each of the numbers can divide into without leaving a remainder. That number is the LCM. We may just look at the options and realize that the correct answer is 36, as well as we may just check them individually to see the ones that 6, 9, and 12 can divide into without leaving a remainder. We may just look at the options and realize that the correct answer is 36. Some candidates should be able to do that. Even from primary school, some students may be able to do that, as well as we may just check them individually to see the ones that 6, 9, and 12 can divide into without leaving a remainder. If we start at A, the first one that we encounter is 36. That is, if we start at A, attempting to find all of the numbers that 6, 9, and 12 can divide into without leaving a remainder, the first one that we will encounter is 36. The options are in ascending order. That means we realize that the numbers are increasing all the time. Therefore, we know that 36 is our correct answer because all of the numbers that come after 36 are greater than 36, and we are looking for the smallest such number. Therefore, we need to go no further. If they were not in ascending order, we could have identified 36 and 72 as the only two numbers that 6, 9, and 12 can divide into without leaving a remainder, of which 36 is the least. The correct answer is therefore option B. Many candidates may say that the problem is very simple. However, in the light of the fact that we are seeing a decline in the number of students who know their multiplication table and how well they know them, some candidates will at least take too long to solve it, wasting precious time in the examination. Do not forget that the ability to work a problem out and get it right is just one thing that determines how well you will do on an examination. The other one is how quickly you are able to go through the question paper. If you cannot do that very quickly, when time is up, you would have just finished 10 problems. Same problem, different treatment. We will now do some refreshers in finding the LCM. We'll use repeated division beginning at the smallest prime number that may go into any of the numbers until the entire set of numbers is exhausted. The table form will help us to do this efficiently. So there is our table, and we have the numbers in the header of the table, the 9, the 12, and the 6. We will now do some refreshers, as we have said before. We will use repeated division beginning at the smallest prime number that may go into any of the numbers until the entire set of numbers is exhausted. The table form we have right here is helping us to do that, and we are saying 2 is the smallest prime that will go into any of those numbers. So let us use 2. What do we know? 2 into 12 is 6. 2 does not divide into 9 evenly. 9 will return as it is, and 6 divided by 2 is 3. Can 2 go again? Sure, we may use 2 again. So 2 can only divide evenly into 6, and the others will remain the same. We are not attempting to get remainders when we do not have even division. In this event, we will just put the numbers, return them in the next row. Now, since 2 is exhausted, we may move merrily to 3. So the next smallest prime number is 3. 3 into 3 is 1. 3 into 9 is 3. 3 into 3 again is 1. And we have a 3 that we may use again. So 3 is the only one that is left, and we are taking a go at it again. And 3 into 3 is 1, and the table is exhausted. The LCM is the product of all of those primes. 2 times 2 times 3 times 3. The LCM is 2 times 2 times 3 times 3, and that gives us 36. Some of the greatest contributions that were made in the development of my mathematical skills were made by my primary school teachers. They gave me a firm foundation. I therefore take the opportunity to thank Mrs. Peterkin, Mrs. Samuels, Miss Grant, and Miss Dobson. Let's go at the problem again. Here is another method that we learned from primary school. This time we will write each of the numbers as a product of its prime factors. So write 6. 12 is, we'll go with 12 first. 12 is 2 times 2 times 3. 6 is 2 times 3. 9 is 3 times 3. Write down all of the prime numbers that we see present there. All of the prime numbers that we see there, 2 and 3. Locate the largest number of 2's. 12 has the largest number of 2's. There are 2 of them. They will be included in the LCM. Then we locate the largest number of 3's. Locate the largest number of 3's. 9 has the largest number of 3's. 2 of them. They are included in the LCM. The largest number of prime factors is used in each case in order to ensure that all numbers can divide into the proposed LCM. For example, if only 1 2 was used, 12 could not divide into the number that we would have received for the answer. So if we just use only 1 2, then we will have what? 2 times 3 times 3, and that would have been 18. And we know that 12 cannot divide into 18. Therefore, in each case, we need to use the largest number of prime factors that are present. Here we have another take. Finally, the lowest common multiple may be found by writing down a reasonable number of multiples of the numbers and identifying the smallest one that is present in all 3 lists. There we have the 3 lists. Lists of multiples of 12, list of multiples of 6, list of multiples of 9. So we need to find now the smallest number that is present in all of the 3 lists. So we have multiples. We are looking for the one that is present in all 3 lists, and we are looking for the smallest such number. So the smallest number present in all 3 lists is the lowest common multiple. Each list represents the set of multiples of the numbers. We have located an item that is present in each list. It is therefore common to all. That common multiple turns out to be the lowest one that meets the criterion. It is the lowest common multiple. So there we have highlighted the lowest common multiple. The LCM is therefore 36. We have the sets P, Q, and S and their elements. Without going through at first all of the elements, the statement of the problem is soliciting the intersection of all three sets, P intersection Q intersection S. The intersection of the three sets is the set of elements that are present in all three sets, or the set of elements common to all three sets. That element is 2. The element 2 is common to all three sets. We do not have another one that is present in all three sets. There is no other element with the same characteristic under these circumstances. The correct answer is option B. Let us attempt to use a Venn diagram in order to solve the problem. There is our Venn diagram, the set P, the set Q, the set S. When inserting information into a Venn diagram, the elements or element of the intersection of all three sets go first. Nice bit of animation there, getting all those 2's to converge into 1 2. There is nothing else because only the intersection of the three sets is needed. In the Venn diagram, the two circles represent set P and Q. If P is equal to factors of 6 and Q is equal to factors of 4, then the shaded region represents what? What do we have represented by the shaded region? Factors of 6 are numbers that can divide into 6 without leaving a remainder. The following set represents factors of 6. Those numbers that can divide into 6 without leaving a remainder. Factors of 4 are numbers that can divide into 4 without leaving a remainder. The following set represents factors of 4. 1 is a factor of every number, and every number is a factor of itself. The shaded region represents the set of numbers that the two sets have in common. The intersection. It is the intersection of the two sets called P intersection Q. The elements that are present in both sets are those two, and that is represented by option B. The answer in option D demonstrates a common mistake that candidates make, that is, of mistaking factors for multiples. And as I said before, a good multiple choice item will contain the answer to the most likely incorrect way of solving the problem. Multiples of 6 are numbers that 6 can divide into without leaving a remainder. The following set represents multiples of 6. Multiples of 4 are numbers that 4 can divide into without leaving a remainder. The following set represents multiples of 4. Notice the elements that are present in both sets. Every number is a multiple of itself and 1. A student considering multiples would have considered intersection of the sets to be the common multiples of 6 and 4. So a student considering multiples would have considered that the intersection of the two sets will be the common multiples of 6 and 4. Bearing in mind that sets of multiples represent infinite sets. So sets of multiples are infinite sets. The set of common multiples will also turn out to be an infinite set, as we have in option D. In the Venn diagram, NP is equal to 5, NQ is equal to 9, and NP union Q is 10. What is P intersection Q? NP is 5, NQ is 9, NP union Q is 10. What is NP intersection Q? Let us go to be true to principle. The general formula for the number of elements in the sections of two intersecting sets is given by NA union B is equal to, if we can remember, NA plus NB minus NA intersection B. So the number of elements in the entire union is equal to the number of elements in A plus the number of elements in B, subtract the number of elements in the intersection of A and B. It may be written in P and Q for this particular problem. It is in A and B. Now we are coining this formula to suit this particular situation, and we will therefore use P and Q instead of A and B. There we have it. What do we have from up here? We have NP is 5, NQ is 9, and the union is 10. The union is 1 on this side, 10. Let us substitute the values in their respective places. NP is 5, NQ is 9, and NP union Q is 10. There. Add the values on the right hand side and transpose the equation. So add these and transpose. So we will have 10 minus 14 is equal to negative of the number of elements in P intersection Q. 10 minus 14 is negative 4. Negative 4 is equal to negative NP intersection Q. So P intersection Q is equal to 4. So the number of elements in the intersection is equal to 4. The correct answer is option A. There we have used a known mathematical principle in solving the problem. However, I always encourage my students to use common sense in solving problems. On the next slide, we will do just that. The mathematical principles, apply them correctly. There is no harm in doing that. However, we may make use of common sense, my favorite. P has 5 elements and Q has how many? 9. Add those numbers and the result is 14. But what do we know? That the number of elements in the union is 10. If we put all the elements together, we get 10. When we consider the total number of elements in the sets taken together, we get 10. Since 9 plus 5 is not merely 10, the excess must represent the number of elements that are shared between the two sets. Hence, the number of elements in the intersection. So, the number of elements that we have in excess will be 14 minus 10, 4, and that will be the number of elements in the intersection. That is all there is to it. The correct answer is option A. The Venn diagram was given to us we have had 2 takes at solving the problem in which we did not make use of the Venn diagram. Let us use it in verifying our answer in order that it does not seem to be a total waste. Maybe the Venn diagram was given to us in order that we may have a diagram for the purpose that we are using it in this particular case, which is to test our answer, or maybe that we could use another method in solving the problem. When completing a Venn diagram, insert the number in the intersection of the 2 sets first. Lovely. NP is equal to 5. Those 4 elements are in the intersection and therefore belong to P also. The number of elements in P only is the difference between that number and those that are in the set P. These are in P, as we can see. Right, P is this set. We have 4 in there already. The total number is 5. Only 1 more is left to go there. 5 minus 4 is 1. And we do the same on the other side, because that 4 is also in the set Q. So the rest will go there. For Q, we will do likewise, finding the number of elements that are in Q only by subtracting the number of those in the intersection from the total number of elements in Q. That's all there is to it. So the total number of elements is 10, and we have no difficulty seeing that 1 plus 4 plus 5 is 10. We see that the total number of elements in the union of the 2 sets is actually 10. There. 5 plus 4 plus 1 is equal to 10. There is nothing to it. U, that is the universal set, is the set of integers. P, the set of positive integers. N, the set of negative integers. When we have these words enclosed in these brackets that we have here, this kind of brackets are we call braces. When we have that, it means the set of. So N is the set of negative integers. Which Venn diagram illustrates the statement, no positive integers are negative integers. No positive integers are negative integers. Which diagram is indicating that? That. No positive integer is a negative integer means that no element of P is an element of N. The sets therefore do not have any element in common. The sets do not have any element in common. This means that the set do not have any intersection. Sets that do not have any intersection or do not intersect are said to be disjoint. When showing disjoint sets in a Venn diagram, we do so by using circles that do not intersect each other. That is the most convenient, that is the best. The clearest indication that sets are disjoint is to separate them like we have right here. The correct answer is therefore option D. Disjoint sets may also be demonstrated by intersecting sets with no element in the intersection. So we may indicate disjoint sets by having the sets intersecting but placing no element in the intersection. That is another way of doing it. In this particular case, no element is in any section of any of the sets. Therefore, the fact that there is no element in the intersection is insignificant. D is the only sensible option. So, in representing sets that do not intersect, that is, disjoint sets, we may what? do it this way and place no element in the intersection. That's another way that we can do it. However, if we look around, there is no element in any of the sets. Therefore, by leaving the intersection empty, we are not making any sense. The best way of indicating this, therefore, since we do not have any element in any section of the set, is to cause the sets to be separated and be what? Apart from each other, as we have in option D. The simple interest on $400 at 5% per annum for 2 years is given by which one of these arithmetic expressions? Which one? We will use the regular formula for calculating simple interest. Simple interest is equal to principal times rate times time. No over 100. The rate is a percentage, a fraction with 100 as its denominator. Dividing by 100 is therefore a redundancy. As long as the rate is included, dividing by 100 is mandatory. Including 100 in the formula is just a bad habit that we have developed over the years. So we do not have to say simple interest is equal to principal multiplied by rate multiplied by time over 100, because rate is a fraction, which is a percentage, a fraction whose denominator is 100. So by putting in the rate, we will place that number 5 over 100 when we do the substitution. Placing this over 100 is a bad habit that we have developed over the years. So all we need to do is principal multiplied by rate multiplied by time. Rate is actually 5 over 100. And what do we make use of? 402 may be treated as fractions whose denominators are equal to 1. Complying with the forms of the options, we may leave the product of the numerators as is, and in the denominator we make use of the fact that any number multiplied by 1 is equal to itself. So there we have it. Any number multiplied by 1, 100 multiplied by 1 is 100, multiplied by 1 again, we have 100, and in the numerator we have 4 times 5 times 2, as we have it right there. And this is exactly option A.